Okay, there we are. Good afternoon, lads and ladies. Today we are going to we're going to do a few things. I want to talk a little bit more about rational functions because I know we were cut short a bit at our last lecture. And then I also want to start moving on to the new material for this week. Now, if you're worried, I am going to extend last week's homework just a couple of days for anybody who wants a little bit more time on it. Because again, the rational function stuff, not super easy. And then this week's material is going to be talking about rational inequalities and other nonlinear inequalities, which means that today is actually where we're going to finish the material that's going to be covered on exam 2. So let me get my screen share going here. Here's our syllabus, and we're very close to exam 2. So today is Monday, and it is the 12th, which means that the test will be next Monday. So let's get this going. This is MAC1140, section 004. Today is the 12th. So first, announcements. Exam 2 will be next Monday, which should be the 17th. Let me see, I see the chat is blowing up a little bit here. It's in your apartment. All right, yeah, so if you have something going on that makes your home not an appropriate workspace for the exam, you'll want to make other arrangements. There is a testing center on Santa Fe's campus that you can use. And you just have to schedule with them ahead of time. So you Google Santa Fe College Testing Center. It's separate from the DRC. It's not associated with the DRC. It's just a testing center. Oh, I see. Okay, yeah. So next Monday, 10, 17, 20. What else were we going to say? Oh yeah, homework 6 will be extended to Wednesday, 10-4. And then there's just one tiny bit of material that we haven't covered yet that's going to be on exam 2, and that's nonlinear inequalities. So today, we'll be talking about rational functions and nonlinear inequalities. Oh, is that the 19th? Sorry, yeah. Thank you. All right. So yes, so exam 2 next week, next Monday. Today we're going to finish wrapping up the material that's going to be on exam 2. And then we will have a review, let's see, I guess Wednesday, next class. There will be a quiz. There will be a quiz associated with exam 2, just like there was for exam 1. And I will get that open later today so you can start working on it. All right. So the best way to study for the true or false questions is to try to deeply understand the concepts. The way the true-false questions work, of course, they can't necessarily be calculation questions because they're just true or false. So the idea there is to try to think of examples and counterexamples. True or false. Every function is continuous. Obviously not true, right? And you can think of some functions that aren't everywhere continuous, that sort of thing. So yeah, as we go through the theorems and the facts, make sure you can think of examples and also counterexamples. That's the best way. All right, is there anything else announcement-y that we need to talk about? I don't believe so. Oh, there was one issue, quick note. Two of the problems in homework 6 had portions which weren't necessarily fair. Asked for the range of a rational function which was hard. So more than two of them asked for ranges. And in general, asking for a range isn't unfair, but in these particular cases, there were two of them that you don't need to worry about, and I will be manually adding points back in to compensate for those. So let me pull those up really quickly so I can show you which ones to not worry about. Oh, shit. Yeah, if you remember the problem numbers, thank you, Lily. These were questions 32 and 33. So don't worry about the ranges there. You can leave that part blank. The other questions that asked for range, you can get the range. It's not difficult from the graph. But those two particular problems, because of the shape of the graph, you would need a little bit of calculus to find the range exactly. And the intent of the author of the textbook was to have you use a graphing calculator and try to guess using the trace function. It's a horrible thing to do. So rather than that, just leave those portions blank. When you get to chapter 4 in the calculus textbook in Calc 1, you will then have the tools to find those ranges exactly. So I'll go over the exact topics that are on the exam on Wednesday, in our class on Wednesday. Of course, I'd be happy to talk about it in office hours also, but yeah, Wednesday, next class is going to be our review. All right. So let's get into it. And I think maybe the thing to do here would be to solve one or two of these exam problems, or not exam problems, homework problems. No, let's not do it like this. All right. So let's come down here to one of these tougher rational function problems. One of these guys would be okay. These are all kind of odd multiplicity things, aren't they? No even multiplicity stuff. It's good, yeah. Let's look at 31. So we want to find all of the intercepts and asymptotes and then sketch a nice graph. We'll talk about the domain and the range. So our goal is to sketch a graph of the rational function r of x equals x squared plus 8x plus 18 over 3x squared plus 24x plus 48. So remember that our procedure for this, we factor top and bottom, cancel any factors that can cancel, making note of what that does to the function. Then we look for vertical asymptotes, domain. We look for horizontal asymptotes, x and y intercepts, and then we sketch the graph. So my first step should be to factor the top and the bottom. To factor the top, I need to come up with two numbers that multiply to positive 18 and add up to positive 8. Can we think of any two such numbers? That's 3x squared, plus 24, I left an x off here, plus 48. So 18, that's 3 times 6 or 2 times 9. How else can I write 18? Is there any way to write 18 as two positive numbers that add up to 8? 2, 3, 4, it's not divisible by 4 or 5. So yeah, no, the top doesn't look like it factors nicely. What about the bottom? So x squared plus 8x plus 18 doesn't seem to factor nicely. We can compute the discriminant, the b squared minus 4ac stuff here, to try and see if this has any real roots or not. But before that, let's see if we can factor the bottom. So here, 3 times 48, what's that? Well, 3 times 40 is 120. 3 times 8 is 24. So that would be 144. Can we think of two numbers that multiply to 144 and add up to 24? Yeah, 12 and 12. So this guy is x plus 12 times x plus 12. All right. So this lets me rewrite r of x as x squared plus 8x plus 18 over x plus 12 quantity squared. So we can do a few things with this. We can find our domain, and we can find any vertical asymptotes. We're also in a good position here to find horizontal asymptotes. What is my domain? Oh, you're right. I'm sorry. I should have factored this by grouping. Let me go back and be less sloppy. Yeah, this is not going to factor exactly like that. I apologize. So this is not x plus 12 times x plus 12. This is 3x squared plus 12x plus 12x plus 48, which is 3x plus, well, we'll write it, yeah, here, which is, so we're going to factor this by grouping. I'm sorry. From the first bit, we can pull out a 3x, and what's left will be x plus 4. And from the second bit, I can pull out, what do we have there? 12. And what's left is x plus 4. So then I get 3x plus 12 times x plus 4. And so this is 3 times x plus 4 times x plus 4. Yeah, not x plus 12. Sorry about that. So Lily, yeah, your answer would be correct from what I had written down here, but I made a mistake there. That denominator doesn't factor as x plus 12 times x plus 12. It's 3 times x plus 4 quantity squared. So r of x here is x squared plus 8x plus 18 over 3 times x plus 4 quantity squared, like that. Yeah, thank you for catching me on that. Sorry about that, guys. Okay, so what is our domain? Remember, the domain of a rational function is always all real numbers except for those which make the bottom 0. So if we wanted to write this out in words, this would be all real numbers except -4, or in interval notation, -infinity to -4, unioned with -4 to infinity. Vertical asymptotes, there's one of them, and it comes from making this bottom piece equal to 0. So that's the vertical line x equals -4. Horizontal asymptotes, we have that 3-case rule based on the degree of the top and the degree of the bottom. Here, the degree of the top is 2, and the degree of the bottom is 2. So we'll take the ratio of lead coefficients. That means my horizontal asymptote is the horizontal line y equals 1/3. I can go after intercepts. The y-intercept is always easy to find. You get that by plugging in 0. R of 0 is 18 over 48. And we can simplify this a little bit. Both are certainly divisible by 2. Both are divisible by, well, let's start with the 2. So if I divide the top by 2, I get 9. If I divide the bottom by 2, I get 24. And I think both of those are divisible by 3. So that's the same as 3 over 8. X-intercepts are going to be a little bit harder to find. No. So if it was x squared plus 4, then plus or minus 2i would be the things that make the bottom 0. But this is x plus 4 quantity squared. So we have to ask ourselves, what makes this 0? And if you imagine plugging in -4 for x, you would get -4 plus 4 all squared, which is 0 squared. So -4 is the root here, and it's of multiplicity 2. Rather than saying this is different from looking at x squared plus 4. Right, yeah, so x plus 4 squared is equal to 0 if x is equal to -4. X squared plus 4 is equal to 0 if x is equal to plus or minus 2i. So there's a big difference between having the square on the outside here versus having the square on the x there. All right. Remember, x-intercepts come from setting the top to 0. And here we said this guy doesn't factor easily, so setting that top to 0 is going to be a little bit of work. X squared plus 8x plus 18 equals 0 I think we're going to need the quadratic formula here because he doesn't factor nicely. So that will be x equals -8 plus or minus the square root of 8 squared is 64 minus 4 times 1 times 18 all over 2, which is -8 plus and minus, let's see, 4 times 18 is 40 plus 4 times 8 is 32, right? So 40 plus 32 is 72, and 64 minus 72 is -8. And all of this is being divided by 2. The square root of -8 can be simplified a little bit. So this is -8 plus or minus I times the square root of 8 over 2. And then that square root of 8, remember 8 is 4 times 2. So I can write this as the square root of 4 times the square root of 2, which is 2 times the square root of 2. So my x-intercepts are at -8 plus or minus I times 2 root 2 all over 2. And for the purposes of the graph, we don't care about these guys because they're not real numbers. So no x-intercepts on the graph. But if you wanted those roots, here's what they are. All right. The only other thing we need then is to start drawing the graph. And I chose this problem because I want to outline something that will be very helpful when we talk about solving rational inequalities, which is our goal for this week, is to learn how to solve rational inequalities. Last thing we need to learn before the test. So I'll mark this as -4 and draw in my vertical asymptote. Label it. I'll mark this as +1/3 and draw in my horizontal asymptote and label it. I have a y-intercept and it's +3/8. Is that larger or smaller than 1/3? Yeah, one way to check this is to look at decimal representations for each. Three over 8 is 0.375, and 1 over 3 is 0.33333. So 3 over 8 is actually a little bit larger. Another way to do that would be to write both of them as fractions with the same denominator. 3 over 8 is the same as 9 over 24. 1 over 3 is the same as 8 over 24. So you'll see that 9/8 is a little bit bigger. So I'll label this as 3/8. All right, it may not seem like we have enough to get a good graph here, but we do. I don't have any x-intercepts over here. I don't have any x-intercepts over here or over here. I know that I need to either approach this vertical asymptote on the right like this or like this. Is the arrow going to be going up on this side or down on this side? I think carefully. Here's a point that I know is on the graph, right? This y-intercept. If the arrow was going to go down on this side, then I would have to cross the x-axis, wouldn't I? But I know that my function doesn't have any x-intercepts, which means it has to go like this. Did everybody follow that logic? This is a little bit sneaky. So just from this y-intercept, I'm trying to figure out whether I approach my vertical asymptote on the right like this or like this. If I was going to approach my vertical asymptote by going down here, to get there from this y-intercept, I would have to go over the x-axis. And I know that I don't have any x-intercepts. So over here, I have to approach like this. Similarly, on this side, I know that I'm going to approach this horizontal asymptote, which is positive above the x-axis. So I can't possibly come down here. It can't be like this, because if it was, I would have an x-intercept, which means I need to be approaching the VA on this side like this, and that means I'm approaching my HA from above like that. Again, over here, no x-intercepts. I'm coming in from above, which means I'm going to settle down on this guy from above like this. So there's your graph. I want you to notice something. This vertical asymptote, x equals -4 right here, came from a multiplicity 2 factor in the denominator. The even multiplicity here and the fact that we didn't go from positive to negative, the fact that we stayed the same sign on either side, is not a coincidence. And this is sort of the last important thing we need to learn about rational functions before we can start talking about rational inequalities. So here's our graph. It's a good graph, we're happy with it. Are there any questions about how we got this graph? Now on a test, I would want you to add in at least 2 other points. We have one point that we know is on the graph here, 0,3/8. And on a test, I would want you to graph for me at least 1 point over here and at least 1 point over here, something like that. I would want a minimum of 3 points labeled, and the instructions will say so. So you could plug in -5, and you could plug in like 2, and give me a few extra points like that. But the interesting feature of this problem that made me choose it is the fact that you have this sort of behavior near an asymptote. You've probably noticed that most of the vertical asymptotes, you'll go up on one side and down on the other. And what I want to do now is discuss the connection between those and the algebra of the function. So if the VA comes from an even multiplicity root of the denominator, then either you will go down on both sides, or you will go up on both sides of the VA. All sorts of other stuff could happen far away from the VA. I don't care about that. I'm just talking about what happens near the vertical asymptote. So these VAs come from even multiplicity factors of the denominator. And then VAs where you change sign, like going up on one side and down on the other, maybe something like this here, and something like this here, or could be the other way. Maybe you go down on the left and come back from above. These sort of behaviors, the VA comes from an odd multiplicity factor of the denominator. So it's very similar to when we talked about the local behavior near roots. You guys remember that? Like whether you bounce or cross the x-axis at a x-intercept at a root depends on whether the multiplicity of that root was even or odd. Well, whether you change sign as you jump over a VA depends on whether the factor downstairs is even or odd multiplicity. If it's an odd multiplicity factor, you will change sign, meaning you'll either go from positive to negative or from negative to positive. If the vertical asymptote comes from an even multiplicity factor, you won't change sign. You'll either go from negative to negative or from positive to positive. This is a big deal. So let me give you something like this. See if we can sketch the graph. Here I've already factored the top and the bottom for you. So that first step is done. The degree of the top is 3, because if I multiplied all this out, I would have x squared plus 4x plus 4. And then when I multiply this x through that, that would begin with an x cubed. And the degree of the bottom is 3, because this guy is x squared minus 6x plus 9. And then when I multiply this x through, he would start with an x cubed. So we're going to run through all the normal stuff. Domain here is all real numbers except for -1 and +3. We can write that in set builder notation as the set of all x's, such that x is not equal to -1 or 3, or in interval notation as -infinity to -1, unioned with -1 to 3, unioned with 3 to infinity. The vertical asymptotes, there are two of them. One of them is the line x equals -1, and the other one is the vertical line x equals 3, again, coming from these two factors downstairs. The horizontal asymptote here is the horizontal line y equals 1, because the degree of the top is 3, the degree of the bottom is 3, and if you multiplied all of this out, both of the lead coefficients are 1. So the degrees match. We take the ratio of lead coefficients. That would be 1/1. I'll write here because r of x, if you multiply everything out, upstairs you would have x cubed plus lower order terms. And downstairs you would also have x cubed plus lower order terms. So the degrees match. You take the ratio of lead coefficients, that's 1/1. X-intercepts, we have several. They come from setting the top to 0. The top is 0 when this piece is 0, which is when x is equal to -2. So I'll write these as points. These are -2, 0, and 1, 0. The y values are 0 there because they're x-intercepts. That's what x-intercepts are. And our y-intercepts, there's only ever one of those. If I plug 0 in for x, the numerator is 0 plus 2 squared times 0 minus 1. The denominator is 0 plus 1 times 0 minus 3 all squared. That's 4 times -1 over 1 times -3 squared is 9. So this is -4/9. Is there anything we're missing here? VA, HA, domain, x-intercepts, y-intercepts? No, we good. Gucci. All right. So I'm ready to start sketching my graph. And I'm going to use everything I know about multiplicities to help me out here. -4/9, that's a little bit smaller than -1/2. So maybe I'll mark this as like -1. So -4/9, my y-intercept is right here. That means I should mark this guy as +1, and I'll draw in my horizontal asymptote. I have two vertical asymptotes. One of them is at -1. Two vertical asymptotes, one here, x equals -1. And then one of them is over here at +3. So I'll go 1, 2, 3, and I'll draw in my other vertical asymptote. X-intercepts, I've got one over here at -2, 0. And I've got one on the right-hand side over there at 1, 0. Okay. Now we're ready to start filling things in. I'm going to start on the far left. I know I have to approach this horizontal asymptote. And the question is, do I approach it from above or from below? So who can help me out? Will I be approaching my HA like this from below or like this from above? Why? Has to come in from below, right? Because I've got this x-intercept down here. That tells me that my function is hanging out down here, below the horizontal asymptote. So I'm going to have to approach from below. And then I need to make my way towards this x-intercept. Now, at this x-intercept, am I going to cross the x-axis or am I going to bounce off of it? I'm going to bounce because that x-intercept is coming from this multiplicity 2 factor. So I'm going to do something here like this. Thus, as I approach this vertical asymptote, since I don't have any more x-intercepts in here, do I approach this VA going up like this or going down like this? Do I approach like this or like this? So remember, I have to depart from this x-intercept going up. If I was going to go down here, I would have to cross the x-axis again, but I don't have any other x-intercepts. Yeah, so it's got to be like this. When I come over the vertical asymptote at x equals -1, am I going to come back from below or am I going to come back from above? This one is above. Oh wait, hang on. No, this one, so I leave going up. This VA comes from this factor. This factor is an odd multiplicity factor. So I will change sign. So I come back from below, right? This is that behavior near asymptotes thing we were just talking about. It's just like the bounce or cross question. You change sign if the factor is odd multiplicity. You don't change sign if the factor is even multiplicity. This VA came from this factor. Since this factor is odd multiplicity, I do change sign as I go over that VA. Another way to think about that is I know that my y-intercept is right here. It's negative, and I don't have any x-intercepts in this portion. If I was coming down from above, I would have to cross the x-axis to get to that guy. But I'm not allowed to cross the x-axis anywhere in here because I don't have any x-intercepts in there. All right, so I know I'm coming back up from below like this. I've got my y-intercept here. At this x-intercept, am I going to cross or bounce? Do I go across like this or do I bounce like this? I gotta cross because he's coming from an odd multiplicity factor. So I can fill in his local behavior, which leads me to this vertical asymptote. Am I going to approach him by going up like this or down like this? Careful, so the 3 isn't an x-intercept, it's a vertical asymptote. But you're correct that we will change sign. We'll go from positive to negative or vice versa. So I know that at 1 I have to cross, and I know that I'm negative coming up to the 1 because this is negative. Since I don't have any other x-intercepts in here, that tells me I have to approach my vertical asymptote like this. And then like Lily said, because that vertical asymptote is coming from this, oh wait, no, this is an even multiplicity factor. So he's not going to change sign. He will be like this. And that tells me that on the far right, I have to approach my horizontal asymptote from above. So this is all the local behavior near the intercepts and local behavior near the asymptotes. This is what we need in order to sketch a good graph of this very complicated rational function. So I'm going to go left to right. I know that I approach this horizontal asymptote from below because I have an x-intercept here, which tells me the graph of my function is below the horizontal asymptote in this region. Coming from there to here, I know that I have to bounce off of this x-intercept because he's coming from this even multiplicity factor. So it's got to be a bounce, and it's an up to up bounce because I'm starting positive over here. Leaving this x-intercept and coming up to this asymptote, the question is, do I go up as I go to that asymptote or do I go down? I know that I'm leaving here going up, and I know I don't cross the x-axis any more times before I get to that asymptote, so I have to approach that asymptote going up. That asymptote came from this factor, which is an odd multiplicity factor, which means I will change sign as I jump over it. I left going positive, I have to change sign, so I have to come back being negative. So that tells me how to fill in this arrow. Leaving this asymptote, I know I have to go over here through my y-intercept, which tells me I have to arrive at this x-intercept from below. I'm negative coming in. This x-intercept came from this odd multiplicity factor. This is a multiplicity 1 factor, which tells me that I'm going to cross there rather than bouncing. That means I know I came in negative, so I have to leave positive, which tells me that I need to arrive at this next vertical asymptote positive. In other words, I have to leave going up. This vertical asymptote came from this factor, which is even multiplicity, which means I will not change sign as I jump over it. I'm positive as I come in from the left, which means I got to be positive as I come in from the right. And then the fact that I'm positive here tells me I'm going to approach my horizontal asymptote from above rather than from below. So this is admittedly a very complicated function, but now that we have all that local behavior in, we can draw a very nice graph. Something like this. And then over here, something like this. All right. I do have office hours today and tomorrow. Yep. So this is as bad as any of these graphing problems can get. I wouldn't give you something like this on a test, but we should be able to work through it one little bit at a time. If you have trouble remembering those rules for asymptotes, the vertical asymptotes, whether you go like this or like this, think about the graph of 1 over x squared and the graph of 1 over x. 1 over x has an odd multiplicity factor downstairs, and he does change sign at that vertical asymptote. 1 over x squared has an even multiplicity factor downstairs, and he does not change sign as you jump over his vertical asymptote. So that's all I want to say about graphing rational functions. But this business of changing sign versus not changing sign as you go over a VA can be very useful for solving inequalities, which is the last kind of new topic. Let me see, how am I doing on time? I'm doing okay. So that's the next thing we're going to talk about, is solving nonlinear inequalities. I'd like to begin with this function. So what if I wanted to solve the inequality x plus 2 quantity squared times x minus 1 over x plus 1 times x minus 3 quantity squared is greater than or equal to 0. The trick to solving this rational inequality and all nonlinear inequalities is to identify anywhere the function is capable of changing sign, which is anywhere the top or the bottom is equal to 0. So the process for solving any nonlinear inequality goes like this. First, you pull everything to one side. And then write as a single fraction by having a common denominator. Here, this has already been done, right? Everything is on one side, the other side is 0. The second step is to factor the top and the bottom. And again, here, that's already done. Then you record any numbers that make the top or bottom 0. I call these the special numbers. Some books call these critical numbers, but critical number means something very specific in calculus, and I don't want to confuse you when you get there. So here we pull everything to one side, put into a single expression, factor the top and the bottom, and then write down any numbers that make either the top or the bottom equal to 0. So for this guy, those numbers would be -2, -1, 1, and 3. Those are the special numbers for this inequality. The next step is to plot the special numbers on a number line. So here's -2, -1, 1, and 3 on the number line. And then the last step is to determine the sign of the function in each region. And you can do this two ways, two options. First option is you can use test points. You can test a number from each region. Or you can use end behavior and multiplicities. And that's it. Then you write down your answer. So we've already done up through step 3. Let me go ahead and do step 4 and 5. Here's my number line. First, I'll do it by thinking about end behavior and multiplicities. So the end behavior for this function, this guy, we know his horizontal asymptote is y equals 1. So here the HA is y equals 1, which is positive. So I know all the way out here on the left in this region, I have to be positive because I'm approaching this line. Yeah, here, I'll give just a second for folks who are writing. Region, R-E-G-I-O-N. Determine the sign of the function in each region. Write down the solution. Yeah, just write down solution. Okay, so remember the inequality we're trying to solve is this one at the very top there. Because my horizontal asymptote is positive, I know that all the way off to the left here, my function is positive because it's approaching 1. As I jump over the feature at -2, that special number at -2, I want to ask, does my function go negative? Is this next piece plus or minus? Does this function right here stay positive or does it become negative? Because the -2 is coming from this even multiplicity factor, I know that I will stay positive. Next, I want to know, what about this region between -1 and 1? In other words, as I jump over the feature at -1, does my function change sign or does it stay positive? Well, the feature at -1 is a vertical asymptote and it's coming from this odd multiplicity factor. Since this factor is odd multiplicity, I will change sign. Good. Now, what about at +1? At +1, will my function change sign or will it stay negative as I jump over this? Well, this +1 is an x-intercept coming from this factor of the numerator, which is an odd multiplicity factor again. So again, I will change sign, going this time from negative back to positive. And then what about at 3? Well, at x equals 3, I had a vertical asymptote coming from this factor of the denominator, which is an even multiplicity factor. And we know as we jump over even multiplicity stuff, we don't change sign. So yeah, in this last region here, I will not change sign, I will stay positive. So now my number line is complete. Remember what I wanted to do was solve the inequality, this shit is greater than or equal to 0. Well, here I have a number line telling me where that function is positive and where it's negative. That function is positive from negative infinity up to -2, from -2 to -1, from 1 to 3, and from 3 to infinity. So I can write down my solution. And now I just have to figure out whether it's parentheses or brackets on each of these. Always a parentheses on the infinity symbol. We can't actually get to infinity. Is my function greater than or equal to 0 at x equals -2? Well, -2 was an x-intercept. X-intercepts are places where the function is exactly equal to 0. So I can include -2. What about -1? Can I include -1? Well, -1 was a vertical asymptote. So this function is undefined at -1. So no, I can't include him. So a parentheses on -1, not a bracket. What about at +1? I know the interval 1, 3 is a part of my solution set. Wait, why is 1 positive? I thought it was negative because odd multiplicity. We change sign when we jump over an odd multiplicity feature. So between so we started positive. We didn't change sign as we jumped over -2 because he came from an even multiplicity factor, so we're still positive. The -1 here came from this odd multiplicity factor. So we did change sign there. When we jump over +1, that comes from this odd multiplicity factor. So we change sign back to positive here. And then at the 3, this is an even multiplicity factor. So instead of changing sign back to negative, we stayed positive here. So I want to make sure I understand the question. What do you mean, Lily? Right. If the multiplicity is odd, you change sign. If the multiplicity is even, you don't change sign. That's precisely the pattern. Cool? Okay, what about Fabrice? You feeling okay? So let's look at the graph. I'm trying to figure out where this function is greater than or equal to 0. So everywhere from -infinity up to -2, my function is above the x-axis. And everywhere between -2 and -1, my function is above the x-axis. And I include the -2 because I'm trying to solve the inequality greater than or equal to 0. So being equal to 0 is okay. From -1 all the way up to +1, that was this region, my function is negative. So I don't include that in my solution. But then from -1 all the way up to 3, my function is above the x-axis. And also from 3 all the way off to infinity, my function is above the x-axis. So do we see from the graph why the solution to r of x is greater than or equal to 0 should be -infinity all the way up to -1. We wrote it as -infinity to -2 bracket union bracket -2 to -1 paren union with 1 to 3 parentheses union with 3 to infinity. Can we see from the graph why this inequality has this solution? The stuff I'm writing here in interval notation is exactly the orange intervals. And the point of this exercise with the number line is to solve this inequality without the graph. And what I'm trying to point out is that if you use that number line and the multiplicities of these factors, the even, odd multiplicities, you can get this solution without the graph. So first, are we comfortable getting the solution from the graph? Just seeing where the graph is above the x-axis? Right. It's not that my function is negative at 3, it's undefined at 3. I can never include a number where my function is undefined. The 2 is a bracket because here being equal to 2 is okay. Or sorry, being equal to 0 is okay. At -2, my function is defined, it's just equal to 0, and 0 is greater than or equal to 0. Same thing at +1 here. At +1, my function is defined and it's equal to 0. 0 is greater than or equal to 0, so I can use a bracket here. The 3's out because my function is undefined at 3. And then otherwise, it's just thinking about these orange intervals. So let's compare this to what we were getting from our number line work. We hadn't quite finished, but you see, right? These are the same things. So we're just trying to figure out whether or not we should include the 1. Yes, you can. You can also plug these into the function and see whether you get something that satisfies the inequality or something that's undefined. 1 is an x-intercept, so he's okay. 3 is a VA, so he's out. Union with 3 is a VA, so he's out. And infinity is infinity, so it's always parens. You see, we get the exact same answer we got from the graph using the number line. But this number line procedure is much faster. Right? Drawing that graph is hard. Even with me writing the instructions and all the steps, it was faster to use the number line. Now, all of this is just assuming you want to use the second option here, end behavior and multiplicities. If you don't like this, the alternative is to test a number from each of these intervals in your inequality and see whether or not it's true. If it is true, yes. If not, then no. Right? If when you plug, say, -3 into your inequality, you found that that function was greater than or equal to 0, I would know to write this plus. When you plug 0 into your inequality from this interval, you would get the y-intercept, which was negative, and so you would know to put a minus. The test point procedure just takes a long time. And that's why I'm trying to show you this trick for speeding things up using multiplicities. So if this is feeling overwhelming, let's look at a simpler example. Let's solve the inequality x minus 1 over x squared is strictly less than 0. Okay. Here, everything's already been pulled to one side. Remember, that's our first step. Pull everything to one side so that there's 0 on the other side. Everything's already been put into this single fraction. And we don't have to do any factoring. So I just write down my special numbers. Those are any numbers that make the top or bottom 0. So what are my special numbers here? One is one of them, but -1 is not. What's the other one? Yeah, 0, right? So the top is equal to 0 if x is equal to 1, and the bottom is equal to 0 when x is equal to 0. We just set the top and bottom equal to 0. Now I draw my number line, and I plot those two numbers. 0 is to the left of 1 on the number line, so I'll put 0 over there and 1 over here. Now for this function, x minus 1 over x squared, the horizontal asymptote is y equals 0, which is neither positive nor negative. So here I will need a test point. So in this far left region, let me test x equals -1. I would get there -1 minus 1 over -1 squared, which is -2 over +1, which is -2. Is that less than 0? It is, yeah. So this region would be a part of my solution set. My function is negative there, and I'm trying to figure out where is this thing negative. So you just write down the sign of this guy. This is negative, so I put a minus here. Now thinking about multiplicities, as I jump over 0, which is coming from this factor, will I stay negative or will I change sign to become positive? What is the multiplicity of this guy? 2, right? And 2 is an even number. So because the multiplicity is even, I will not change sign. I will stay the same sign. So here I was already negative, so I'm going to be staying negative. So you're right that we'll stay. It's just that the thing we're staying is negative. We were negative over here. So when I jump over, I will remain negative. And then this fellow is coming from the top factor, which is odd multiplicity, right? This is the same as that. So as I jump over 1, will I stay negative or will I change to positive? So is the multiplicity even or odd? Remember, that's the thing that matters here. And as we jump over odd multiplicity features, we change sign, right? This would be a cross rather than a bounce. So this is going to change to plus. So even multiplicity, you stay the same sign. And odd multiplicity, you change sign. So this guy came from an odd multiplicity factor, so I changed sign. This guy came from an even multiplicity factor, so I stayed the same sign. Is it starting to settle? Exactly, yes. Which is why we had to test a point over here, or why we had to use the horizontal asymptote in the previous example. As soon as you know one of the regions, you can get all the others using the multiplicity trick, but you have to know the guy next to him in order to figure out. So if you're jumping over an odd multiplicity thing, you'll change sign. If you're jumping over an even multiplicity thing, you'll stay the same sign. But yeah, you got to know the neighboring region to get the region you're on. So I know I started negative. As I jump over this, I'll stay the same. So I stay negative. Now I know here I'm negative. As I jump over this, I know I'll change sign, so I become positive. So the solution set here is negative infinity up to 0. I can't include 0 because he's undefined at 0. So parentheses, union, 0 to 1. And can I include 1? No, because here I'm asking for strictly less than 0. So this is my solution set. Yeah, so in this first guy, I tested a number. I just grabbed a number that is in this region and I plugged it into my function. And if you're ever worried that you made a mistake using the multiplicity trick, you can test a number from every region. I could plug 1/2 in to verify that my function is negative here. I could plug 2 in to verify that my function is positive over here. And that's it. That's the game. That's how we solve nonlinear inequalities. So you have to ask, to determine whether or not to use the bracket or the parentheses, you have to ask whether that endpoint satisfies your inequality. Here I have a strict inequality. So when I go to plug in 1, I get 0 over 1 is less than 0. Well, 0 over 1 is 0, and 0 is not strictly less than 0. So if you have a strict inequality, like strictly less than or strictly greater than, it will always be parentheses. If it's less than or equal to or greater than or equal to, then the special numbers that come from the top will have brackets, and the special numbers that come from the bottom will have parens. Right, so the only time you'll see brackets is in a weak inequality, less than or equal to or greater than or equal to. All right, this is all we have time for today. I want to thank you guys for working through these with me. I know that the first problem, especially here, was quite challenging, and I'm very proud of you for sticking through and asking questions. That's great. You'll have a homework set and a quiz opening up today. The homework set will have a little bit more rational function stuff like these inequality problems, but it will be a short homework set. And then the quiz will have problems of all sorts that are going to show up on the test. Both of those will be due next Monday, a week from today at the start of class. And next Monday is your exam too. So Wednesday of this week, our next class is going to be a review for the test. And then the test will be the following Monday. A quick note before I let you go. The examples that we did today where we solved these rational inequalities, the first few steps were already done for us. We had everything already pulled to one side. We had everything already written in a single fraction, and we had everything already factored. That's where the majority of the work is in these problems. The number line stuff is usually fairly quick. Once you get used to it, it goes very, very fast. So most of the work in these is algebra manipulations to pull everything to one side, have a single common denominator, and then factoring the top and bottom. But that's all stuff that we've done before. You've got practice having common denominators, and you've got practice factoring polynomials. That was the whole last homework set. So take your time on the homework problems that are coming out this week, then get to the quiz. And if you have questions on anything, you get stuck on anything, please come by office hours or take a picture, send it to me through email or a Canvas message, okay? All right, I gotta get running. I will see you guys either in office hours or on Wednesday when we review for the test. Take care.